Right, so here's the big picture for chapter 2. And notice there's a place on the beginning of your notes paper for you to write some notes in here. We said today that using that variable h and letting it stand for a small number that we're going to let get smaller and smaller is a little bit of an introduction to the idea of a limit. And that limits, we need to have an understanding of the language of limits before we can even create calculus. So chapter 2 is all about limits, and then once we have that set, we're going to talk about what we can do with limits, which actually is the body of first semester calculus starting in chapter 3. So we are going to think about limits of functions using substitution, using graphs, using tables, and using algebra. So some of this we've tried already. We were thinking about trying to find the average speed of something that's moving, but finding its average speed over a time interval that was really, really short. In fact, we wanted a time interval of 0, like 0 seconds between the two times. We tried using substitution in that case, and it wouldn't work because we needed our h to be 0, and we can't divide by 0. We're going to talk about some other limits that we can simplify with substitution. We didn't use a graph so much already, but we did use a table. Remember when we were trying to compute the instantaneous speed of that rock falling from the cliff, and I showed you how I used time 2 and time 3, and then time 2 and time 2.1, and time 2 and time 2.001, and I let that small change in time get smaller and smaller. I was using a table to see what would happen to the output when I let that small change get smaller and smaller. And then once we decided we wanted to have something more concrete, we used algebra. We expanded that expression in the numerator. We were able to factor out an h and cancel. That's using algebra to explore limits. So you're going to see all 4 of those in this chapter. Big idea that sometimes confuses students, so I want to nail it down right at the beginning. Limits are about describing the behavior of a function given a certain input value. So we're going to be exploring the outputs of the function. The limit is the output. It's like the y value. I'm going to tell you what x value I'm interested in exploring at or near, but a limit is always an output value. It's always a function value, never an x value. It's always a member of the range, not a member of the domain. And last big idea, we're learning about limits because we need limits to understand continuity, which comes up in section 2.3. And without continuity, we can't build calculus. We're going to find, once we understand what continuous functions are, that the calculus we try to do, we can only really guarantee applies to continuous functions. So that's the big picture for chapter 2. Before we move on to the next, there's a place for you to remember how we compute average speed, and then to describe how to compute instantaneous speed. So you're going to write those in, and then I'm going to jump down here. We're going to start exploring the limit of a function you probably haven't ever seen before. Okay, you'll recognize this as the slide from the last video where we did all that algebra to make it so that we can actually compute instantaneous speed for the rock falling from the cliff. That's because when we chose one algebra path, which is to expand that numerator, combine like terms, and then factor and cancel, we're able to rewrite this expression in a way that didn't result in division by 0, which meant that we could think at the very, very end about replacing h with 0 without anything breaking. So that was an informal description of the process we use. But it's exactly the process we use, which is to think about what would happen to that computation if h got closer and closer and closer to 0. So now I'm going to introduce, it's the exact same math, the exact same process, but instead of just labeling over here instantaneous velocity and then saying it's approximately equal to this, I have a notation that means we don't have to use the approximately equal sign anymore. So I wrote over here so you can kind of see how we read this. I would read this: the instantaneous velocity is equal to the limit as h approaches 0 of, and then I could read this big expression. I'll read this last line down here. The instantaneous velocity is equal to the limit as h approaches 0 of 64 plus 16h, which, since there's no danger now in letting h actually equal 0, I can treat h as if it were 0, and that's why I substitute 0 in for h. The 16h term disappears, and I can say that the instantaneous velocity is exactly 64 feet per second. So it's this notation that's one of the key topics. That's like a key part of your first test. We're going to practice that notation. We're going to practice writing it. We're going to practice reading it. We're going to practice solving problems that involve this notation. All right. So I want to talk about a new function. I don't expect it's something you've ever seen before. It's just kind of like a made-up function, but I want something that we haven't talked about before so we can come at this idea of a limit with a fresh start. So if I just gave you this function, y is the sine of x divided by x, and I said, what's y when x is 0? You would have to say, Mrs. Hicks, there's no way I can answer because I would be dividing. Sine of 0 is 0, and x would be 0, so I'd have 0 divided by 0, and division by 0 is undefined. So it turns out that's totally true. Y is completely undefined when x is 0. If we graph this function by hand or on a really sophisticated calculator that doesn't accidentally fill in spots, there would be a hole, like a 1 pixel wide hole at the place where x equals 0. But we can still talk about the answer to this question, which is what happens to y as x gets close to 0. So that's what we're going to explore. We said we can explore limits with graphs, tables, algebra, and substitution. So let's explore this one with a graph. Probably you've never seen that graph before, but there's the graph of sine of x divided by x. And if you can imagine, at the place where x equals 0, which is at the y-axis, so right here, if I look at my graph, I'm looking at that point. Could you tell me what the y value is? Well, it looks like, if I read that graph really carefully, it looks like the y value is supposed to be 1 when x is 0. Now, it can't actually be 1 because when x is 0, y is undefined in this case. But from that direction and from that direction, if I walked along this graph and I could see the path ahead of me and you asked me where I was headed, I would guess I was headed toward the y value of 1 if I was walking from this direction. And you asked me where I was headed, I would tell you my y value is getting closer and closer to 1. So this is like that our first understanding of the limit of a function where we know that function cannot be defined. What about if I wanted to use a table? I'm going to use a table to explore the same limit. So how does this function behave when x gets close to 0? So this is a feature your calculator has. You can tell it how far apart you want these numbers. You can make sure you have some number that you're interested in, some x value you're interested in, make sure that's there in the table. And you can see as you have numbers to the left, just to the left of 0, and you use them for your x's, -0.3, -0.2, -0.1. Check this out. These numbers get closer and closer to 1. The table doesn't go on that long, but I'll tell you that if you came from this direction, this was 0.2, 0.3, but as you got closer and closer to 0 in this direction, those y values get closer and closer to 1. So we're going to start to think that maybe the limit as x approaches 0 of sine x over x is 1. It's the y value that should be there, even if I can't ever really quite get there, because as soon as I walk into the place where x equals 0, there's a hole in the graph. So notice here, I just read limit as x approaches 0 of sine x over x. It's totally equivalent to saying the limit of sine of x over x as x approaches 0. When you describe a limit, you have to say the function whose limit you are exploring, and you have to say the x value you're interested in x getting toward. All right, so we tried substitution, but it didn't work for us here because we ended up substituting in 0 and ended up dividing by 0. But we did use a graph, and we used a table of values to investigate the limit of the function sine x over x at the place where x equals 0. And our conclusion is, at least as far as we know right now, it seems like that limit is 1. It is, in fact. If you are interested in exploring that algebraically, your textbook has a section on the sandwich theorem, which you can explore, but it's not a topic that is required for the AP Calculus test. So, new notation. Here we go, and then there's a place for this on your handout. This is limit notation. It's a big deal. You have to know it by the time you take your first test. You have to know it by the time you sit down for the AP test. I say the limit as x approaches, well, I'm going to read it this way. The limit of f of x as x approaches c is L, which is completely equivalent to saying the limit as x approaches c of f of x is L. That's probably the way that I am just used to reading it, because it kind of feels like I'm reading more left to right. They are totally equivalent. But you have to name the x value you're going to approach, and you have to name the function that you're taking the limit of. So the notation I would use, which is what you see on your paper for 5A, I would say the limit of sine x over x as x approaches 0 is 1. Because 1 is the y value that this function should have if something weird hadn't happened and like made that point disappear at the place where x equals 0. So this is our brand new notation. We're going to spend the whole rest of chapter 2 making sure this notation sticks in, and then using that notation to have a very clear definition for the idea of continuity.